You're walking on a frozen sidewalk, your foot hits ice. Instantly you're sliding, zero traction. Maybe you catch yourself, maybe you fall. Either way, you know with absolute certainty that ice is slippery. And if someone asks you why, you probably say something like, pressure from your foot melts the ice, creating a thin water layer, and water is slippery. This explanation is in textbooks. It's what teachers tell students. It sounds perfectly reasonable, and it's completely wrong. The math doesn't work. The physics doesn't support it. Scientists debunked this theory decades ago, but somehow it persists in popular understanding. The truth is far more interesting. Ice is slippery because of broken symmetry at the molecular surface. Emmy Noether's principles explain why surfaces must behave differently from bulk material. And once you understand the real mechanism, you'll realize that ice skating, glacier movement, and even planetary science all depend on a phenomenon that most people fundamentally misunderstand. Today I'm going to show you why everything you learned about ice friction is wrong and what's actually happening at the molecular level when you slip. Before we shatter the ice mythology, I need to know, are you watching this on your phone while it's cold outside, on your laptop during winter, or on your TV in a warm room? And more importantly, have you slipped on ice recently? Do you ice skate? Have you ever wondered why ice skates work but snow boots don't? Drop a comment below and tell me your relationship with ice, because I'm genuinely curious if people who interact with ice more frequently have better intuitions about this. Also, tell me what you currently think makes ice slippery, because I want to know how deeply the wrong explanation has penetrated. Let me start with the theory everyone knows and why it sounds so convincing. The pressure melting theory goes like this. Ice melts at 0 degrees Celsius under normal atmospheric pressure, but if you increase pressure, you can lower the melting point. This is unusual. Most materials have higher melting points under pressure, but water is weird. Its solid form is less dense than its liquid form, which means pressure favors the denser liquid phase. So the theory says when you step on ice or skate on ice, you're exerting pressure. That pressure locally lowers the melting point. The ice directly under your foot melts, even though the ambient temperature is below 0. You're now standing on a thin film of water. Water has low friction. You slide. When you lift your foot, the pressure disappears. The water refreezes. This explanation has everything. It uses a real property of water. It provides a mechanism. It matches our experience that we slide on ice, and it was proposed by James Thomson in the 1850s and supported by his brother Lord Kelvin, major names in physics, so it became gospel. Textbooks repeated it for over a century, but here's the problem. Nobody actually checked the math carefully until the 1990s, and when they did, the theory collapsed. Here's why pressure melting doesn't work, and this is where the math gets beautiful and damning. The Clausius-Clapeyron equation tells us how much pressure you need to lower ice's melting point by a given amount. It turns out you need about 130 atmospheres of pressure to lower the melting point by 1 degree Celsius. Now let's think about ice skating. A typical ice skater weighs maybe 70 kilograms. The blade of an ice skate in contact with ice is about 2 millimeters wide and maybe 15 centimeters long. That's a contact area of about 3 square centimeters. Pressure equals force divided by area. 70 kilograms of force over 3 square centimeters gives you roughly 23 kilograms per square centimeter. Convert that to atmospheres, and you get about 50 atmospheres. So a skater exerts roughly 50 atmospheres of pressure, according to Clausius-Clapeyron, that should lower the melting point by less than half a degree. If the ice is at -5 Celsius, you'd need to lower the melting point by 5 degrees to create melting. That requires over 650 atmospheres of pressure. An ice skater doesn't come close. Not even a heavy person on very thin blades. The math simply doesn't support pressure melting as the primary mechanism, and it gets worse. People skate on ice at -20 Celsius, -30 in some places. You'd need thousands of atmospheres to melt ice at those temperatures. Impossible with body weight. So if pressure melting isn't the answer, what is? Here's what's actually happening, and this is where Emmy Noether's symmetry principles become essential. Think about ice at the molecular level. Ice is a crystalline solid, water molecules arranged in a regular hexagonal lattice. Each water molecule is hydrogen bonded to 4 neighbors in a tetrahedral arrangement. This structure has translational symmetry. If you move through the crystal in specific directions, the pattern repeats perfectly. Noether's theorem tells us that translational symmetry gives rise to momentum conservation. But here's the key. This symmetry only holds in the bulk of the ice, in the interior where every molecule has a full set of neighbors. But what happens at the surface, at the ice-air interface? Molecules don't have neighbors above them. The symmetry is broken. A surface molecule might have only 3 hydrogen bond partners instead of 4. It's in a different energy state than a bulk molecule. It's more weakly bound, more mobile, and this broken symmetry fundamentally changes the properties of surface molecules. They behave differently. They must behave differently because the thermodynamics of a surface is different from the thermodynamics of bulk material. This isn't speculation. This is mathematical necessity. When you break translational symmetry, you create a new phase. Let me make this concrete. In bulk ice at -10 Celsius, every water molecule is locked in place, vibrating around a fixed position in the crystal lattice. The system is in its lowest energy state given the temperature and pressure, but at the surface, molecules have unsatisfied hydrogen bonds dangling into the air. This creates excess surface energy. The system can lower its total energy by allowing surface molecules to become more mobile. They're not quite liquid, they're not quite solid. They're in an intermediate state that physicists call a quasi-liquid layer. This layer is maybe 10 to 100 nanometers thick, depending on temperature. The molecules in this layer are more disordered than bulk ice, but not as disordered as liquid water. They have liquid-like mobility, but ice-like density. And this quasi-liquid layer exists even without any applied pressure. It forms spontaneously because broken symmetry at the surface demands it. This is the layer that makes ice slippery. You're not sliding on melted ice. You're sliding on structurally disordered surface molecules that have enough mobility to provide lubrication. Noether would recognize this immediately. Break the symmetry, break the crystalline order, create a new phase. Now here's where it gets counterintuitive, and this is my favorite part. If the quasi-liquid layer is what makes ice slippery, then ice should get more slippery as temperature increases toward the melting point, right? Because warmer means more molecular mobility, means thicker quasi-liquid layer. But experiments show the opposite. Ice friction actually increases as you approach 0 degrees. Olympic ice rinks keep their ice at around -5 to -7 Celsius because that's the optimal temperature for skating. Too warm and friction increases, skaters slow down. Too cold and the ice gets brittle and also has higher friction. Why does this happen? The answer is that the quasi-liquid layer can become too thick when the layer is very thin, 10 to 20 nanometers. Your skate blade can shear through it easily. The molecules flow around the blade, you get excellent lubrication, but when the layer gets thicker, closer to 50 to 100 nanometers as it does near the melting point, the layer starts behaving more like bulk water, and water actually has higher viscosity than the quasi-liquid layer. Viscosity creates resistance, so there's an optimal temperature range where the layer is thick enough to provide lubrication, but thin enough to remain low viscosity. Too cold, the layer is too thin. Too warm, the layer is too thick and too viscous. The sweet spot is around -5 degrees Celsius. This is why ice hockey and speed skating are done on ice maintained at specific temperatures. It's not arbitrary, it's optimizing the thickness of the symmetry-broken surface layer. Let me show you the experimental evidence, because this isn't just theory. Researchers using atomic force microscopy can literally measure the properties of ice surfaces at the nanometer scale. They've imaged the quasi-liquid layer directly, they've measured its thickness as a function of temperature, and they've confirmed that it exists even at -30 degrees Celsius, with zero applied pressure. Other experiments use laser spectroscopy to probe molecular dynamics at ice surfaces. They can watch individual water molecules moving in the quasi-liquid layer. The mobility is orders of magnitude higher than in bulk ice, but still lower than in bulk water. It's a distinct phase. Furthermore, scientists have done ice friction experiments where they carefully control pressure and temperature independently. If pressure melting were the mechanism, friction should decrease linearly with applied pressure, but it doesn't. Friction is almost independent of pressure over a wide range. What matters is temperature. Temperature controls the thickness of the quasi-liquid layer, and that controls friction. Pressure melting plays at most a tiny secondary role. The primary mechanism is symmetry breaking at the surface. Now let's talk about why this matters beyond ice skating. Glaciers move because their bases are slippery. Traditional theory said the pressure from kilometers of ice above melts the base, creating a water layer that lubricates glacier flow. But measurements show that many glaciers flow even when the base is well below the pressure melting point. The quasi-liquid layer explains this. You don't need bulk melting, you just need surface disorder. Similarly, planetary scientists study ice on Mars, on Europa, on Enceladus. These moons have surface ice at temperatures of -100 Celsius or colder. Pressure melting is irrelevant at those temperatures and pressures, but surface pre-melting still occurs. Quasi-liquid layers still form, and this affects everything from crater formation to potential subsurface oceans. Understanding that ice surfaces are fundamentally different from ice bulk changes how we model planetary processes, and it all comes back to Noether's insight. Symmetry breaking creates new physics. Here's the deeper principle, and this applies to far more than just ice. Every surface breaks symmetry. Think about it. A surface is by definition a boundary where the environment changes discontinuously. On one side you have material, on the other side you have air or vacuum. This breaks translational symmetry. Anything that breaks translational symmetry must have different properties than the bulk. Because Noether's theorem connects symmetry to conserved quantities, when symmetry is absent, the conserved quantity changes. In the case of surfaces, the missing symmetry means surface molecules have different binding energies, different vibrational modes, different chemical reactivity. This is why catalysis happens at surfaces, why crystal growth starts at surfaces, why corrosion attacks surfaces first. Surfaces are where the interesting physics happens because surfaces are where symmetry is broken. And ice is just one example. Many materials form quasi-liquid or amorphous layers at their surfaces even below their bulk melting points. Lead does this, gallium does this, certain polymers do this. It's a general phenomenon rooted in the thermodynamics of symmetry breaking. Emmy Noether didn't study ice specifically, but her theorem predicted this behavior: break the symmetry, change the phase, create new properties. Let me address one more thing, because people always ask, if pressure melting isn't the main mechanism, does pressure do anything at all? Yes, but it's subtle. Pressure does slightly increase the thickness of the quasi-liquid layer, not by lowering the melting point, but by affecting the energy balance at the surface. Higher pressure slightly favors the denser liquid-like state over the less dense ice-like state, even in the quasi-liquid layer. So an ice skater's pressure does contribute maybe 10 or 20% to the total lubrication. But the bulk of the effect, 80 to 90%, comes from the quasi-liquid layer that would exist anyway. This is why you can slide on ice even with very light pressure. A child ice skating exerts far less pressure than an adult, but still glides easily. If pressure melting were dominant, heavy adults would skate great and light children would struggle. But that's not what we observe. Friction is remarkably independent of weight over a wide range. What matters is having smooth blades that can skim across the quasi-liquid layer without breaking through to rough ice beneath. Blade design matters, temperature matters, pressure is secondary. So why is ice slippery? Not because pressure melts it, not because of a water film created by compression. Ice is slippery because surface molecules exist in a broken symmetry state. They can't maintain the perfect crystalline order of bulk ice because they're missing neighbors. Thermodynamics demands that they minimize energy by increasing disorder. They form a quasi-liquid layer that's neither ice nor water, but something in between. This layer has low viscosity and high molecular mobility. When you slide across it, your shoe or skate shears through this layer with minimal resistance. You're not skating on water. You're skating on symmetry-broken molecular disorder. And this layer exists at temperatures far below the melting point. It exists with or without pressure. It exists because surfaces must be different from bulk. Emmy Noether's theorem guarantees this. Translational symmetry is broken at interfaces. Broken symmetry creates new phases. New phases have new properties. Ice is slippery because physics demands that surfaces cannot be the same as interiors. Next time you slip on ice, don't curse the water that isn't there. Appreciate the quasi-liquid layer. Appreciate the broken symmetry. Appreciate that you're experiencing Noether's principles made manifest in a winter sidewalk. Textbooks lied to you, but physics never does. If this changed how you understand ice and surfaces, please hit that subscribe button, because I'm correcting scientific misconceptions through Emmy Noether's lens. And I want to hear from you. What should I tackle next? What everyone gets wrong about why the sky is blue? What everyone gets wrong about batteries dying at 20%. What everyone gets wrong about how soap cleans. Drop your suggestions in the comments and tell me if you'll ever look at ice skating the same way again. Thanks for watching, and remember, when symmetry breaks, new physics emerges.